Welcome to our next video for Stat 420. In this video, we're going to be talking about model diagnostics for linear modeling. So we've already kind of started talking about this earlier in the course, but now we're going to talk about kind of how we check these assumptions and decide whether they seem sensible to make or whether we might have some assumption violations. So as a reminder, we're doing linear modeling. There's kind of four assumptions. These could be kind of broken out a little bit differently. You could even turn into five if you want to. But the book we're using, we just kind of listed as four things. And they make this nice acronym line that's easy to remember. The first is linearity, which I think is kind of obvious what it means. It means that if we're fitting a relationship between a predictor and a response and we're using a linear term, then the relationship should kind of look linear when we look at that scatter plot, right? So I could have a scatter plot that looks like this, where maybe my relationship between predictor and response isn't quite, maybe it's a little bit more curved like this. And I could certainly fit a line onto this relationship. I can find a best fit line, and this line is certainly doing better than nothing. It's certainly doing better than just like the mean of y as a prediction for y. But we also are going to recognize that this just isn't what the relationship is, and so maybe we shouldn't do that. So this first assumption is just kind of, maybe it seems silly that we need to say it, but that linearity makes sense if we're going to add a linear term to a model for a predictor to the response. The second we'll talk about more, and that's just independence of the residuals, which kind of just goes along with independence between the observations that we're collecting, that we have kind of this random independent sample of the population we're representing, or if it's not random, that at least it's representative and that our observations are independent of one another. Third is normality of the residuals for any given predictor value. So if I kind of think about a cross section of my scatter plot, so for any given kind of x value, I'm looking at the distribution of the residuals, and it should be normally distributed about my best fit line with some kind of variance there, representing how much variability I see in the residuals. Equal variance, again, is kind of what it sounds like. It means that the variance in our residuals is equal at all predictor values, that the variance is not changing, say as one of the predictor values increases. So yeah, it's kind of a quick introduction to the four things. I do have them kind of listed across these next slides for a little bit more detail. In particular, independence I want to talk about a little bit. So independence is not something that's always easy to think about. Linearity is something that just kind of stands out to us on a scatter plot. Like, we're going to know if that doesn't make sense if we look at a simple relationship. Independence, though, is often going to be more a contextual thing. We just kind of have to know the data, where it comes from, and whether this is actually true. It's not something we're always going to be able to kind of see when we look at our data. So two common situations where independence does not really make sense is when we have time-related predictors where the data we're collecting is kind of sequentially collected. Now, if I have like a kind of this population of time, and I can kind of randomly sample different times, that would be one thing, and that would be fine. But usually when we have a time-related predictor, we're collecting data sequentially such that this observation is actually going to be dependent on what happened at the previous observation at this previous time point. So when that happens, I really don't have independence in my observations. My residuals are not going to be independent. Instead, usually I'm going to have kind of this like trend that looks something like this. So this would be an example of data. I think this looks like furniture sales charted over time. So me trying to make some kind of linear relationship with date as a predictor of furniture sales might be a little bit iffy to do, because my data is not going to be, my observations are not independent of one another. Instead, they're going to kind of depend on what's going on at the time point before. And in particular, this is kind of this cyclic relationship where I can't just look at, days after this point, but instead it's going to be a very seasonal kind of relationships. So time series is the field of study that's all about looking at time-related data and modeling trends. So it's a very different approach than, say, the methods that we're using with linear modeling. We're just using kind of information as an input to predict the response, and we're not using complex enough terms. Like, we're just using linear terms. We're not using terms that are going to be able to kind of hit these nuances appropriately. So that would be an example that maybe independence of residuals does not make a lot of sense. Secondly, is when we have multiple observations from the same person, the same unit, the same location, and that would be kind of this nested data situation, meaning that I don't have 100 observations from 100 people, but maybe I have 100 observations from 10 people, where each of these 10 people produced about 10 observations for me, right? That's a big independence violation right there, and it means that I can't necessarily assume that the distributions of data that I have at any given x value are truly normally distributed and represent independent observations from that population, from that y given x population. So whenever you have kind of this nested data situation, hierarchical linear modeling is probably what you're looking for, because that's going to be a model that preserves kind of the nested nature of the observations. All right, normality and equal variance are going to be two things that we can kind of check when we look at the data, though. So independence is more contextual. Normality and equal variance is going to kind of show up when we investigate the plots. So normality, again, as we talked about before, is an assumption we make with the inferential methods that we use, meaning that if I'm making a confidence interval for y given x, I am kind of assuming that the residuals are normally distributed, because if that's not true, then my inferential methods may not do exactly what I think they're doing. My 95% confidence interval may not actually be 95% confidence anymore. So that's somewhat important, though I will kind of mention here, normality is a weaker necessity, and that's because if I also have a really large sample, so I'm just going to say or large sample, I can still do confidence intervals for my beta coefficients. I can still do confidence intervals for the mean of y given x with some level of trust because of the central limit theorem. So if you remember the central limit theorem, it says that the distribution of possible sample means will distribute normally, even if the variable that data comes from is not normally distributed as a population. So because of that, I can actually still do inference in these situations if I don't have normality, as long as I have a large enough sample size to compensate for that. Now, we can't really put a benchmark on it. You might hear things like n equals 100 or n equals 200. Those are things that make life a little bit easier for us if we pretend like we have a benchmark and everything's okay beyond that. But really it just depends on how skewed the distribution is to begin with, how skewed those residuals are, because the more skewed they are, the larger the sample would need to be to compensate. So I'll just kind of leave that very vague and just say that the larger the sample we have, the less we need normality in the residuals, the farther we can deviate from normality and still be okay with some of these inferential methods. Equal variance, though, does need to be kind of addressed, though. And that's this idea that the variance in the residuals is the same regardless of what predictor values we're plugging in, that I still have the same amount of kind of variability, the same amount of error at any given set of predictors. So when this is not true, our estimation is going to be kind of wildly unreliable, and the assumptions we're making about the residual standard error is just kind of weird, because it's not a constant value, but instead it's kind of this average value, and the true variance is quite different at different predictor values. So that's something that we'll talk about more when we get to transformations in the next chapter, I believe. But something that we do want to kind of be on the lookout for now as part of our model diagnostics. All right, so if we're only looking at simple linear relationships, Diagnostics are pretty easy because I can just look at a scatter plot of my x and y variables and usually kind of notice these things. However, whenever I'm doing multiple regression, I have multiple predictors. I don't necessarily want to look at every scatter plot of each of my predictors to the response. And even that isn't quite doing the same thing because really what I want to do is look at the residuals. I want to know that my residuals are normally distributed and that my residuals have a constant variance. So one common visualization method is a residual plot. Because regardless of how many predictors I have, I can always look at the distribution of my residuals on a residual plot. And so what I would do here is I would plot my fitted values on the x-axis and my residual values on the y-axis. And then I would just draw a horizontal line at h equals 0 to kind of represent this is residuals equals 0, and I want to see how the residuals are distributed about that line. Now, that said, I do accompany each of these with an example of a simple linear regression plot so you can kind of see what's going on and how this relates. But again, kind of the real advantage of these is when I'm doing multiple regression and I have multiple predictors and I can't just look at a scatter plot because if I could, well, this is really telling me pretty much everything I need to know anyway. But when I have multiple predictors, I kind of need to do something like this to see what's going on. So here's an example of data that's very linear. The variance looks very constant, and I can see that reflected in the residual plot. My residuals have a constant variance and appear to be pretty normally distributed about that best fit line. Here's an example where that's not going to be true. Instead, I look at this residual plot and I see this cone shape. The residuals are actually changing depending on the fitted value. So if this is kind of my estimate for y, I see that for larger estimates of y, I have a lot more variability in the actual data, and a lot more variability here in these residuals when I think the best fit is actually a higher value. So that tells me that I don't have constant variance in this model and that the variance actually depends on the predictor values. Here's an example of data that's just not linear. It's more curved, and I can see that very clearly in the residual plot that, again, depending on what my estimate is for y, depending on my fitted value for y, the residual is going to be kind of systematically different. That I'm kind of systematically, consistently overestimating the fit here, underestimating the fit over here, and my residuals are not normally distributed about this best fit line, telling me that maybe this is not a linear relationship. There's also QQ plots. To be perfectly honest, I prefer residual plots over QQ plots, but it's just kind of another thing that you should be exposed to probably. And that is looking at the quantiles, both theoretically, what they should be. In other words, if we kind of take all of our residuals and sort them from smallest to largest, we're going to have residuals with the largest negative distance, and then residuals with the largest positive distance, and then in the middle are the residuals that are close to 0. And then on the y-axis, we plot kind of approximately how they should be positioned if the residuals were normally distributed. We can create a QQ plot by using the QQ norm function and plugging in the residuals of our models. We can add the line by doing the same thing, and then there's some kind of formatting over here if you want to add some. Now, it's perfectly normal to see a little bit of kind of local bendiness, I'll say, in a QQ plot. That's okay. What we're concerned about is when we see a systematic divergence from that line. When we see a systematic divergence, especially some trailing off on one end or the other end, that tells us that there might be something suspect with our normality assumption. Here's an example of data that is normally distributed about the best fit line, and we see that with this kind of matchup between the theoretical quantiles and the sample quantiles. This is working out pretty well. Here's an example of heteroscedastic data where we see that kind of systematic divergence on both ends of our QQ plot, which is just kind of showing that the residuals are going a little bit crazy over on the ends at the residuals with the kind of the farthest distance from the best fit line are even farther than a constant variance normal distribution should look like. Here's an example of data that just isn't fitting a line, and you see this kind of steady divergence from that line here. A little bit up here as well, but certainly over here, just kind of suggesting that we have a lot of residuals that are really under the best fit line, and that they don't really make a lot of sense in terms of position if this was kind of consistently distributed throughout. So in addition to these kind of visualization methods, we can also put a probabilistic calculation on this as well. We can use what's called a Shapiro-Wilk test for normality. We can use what's called a Bruch-Pagan test for constant variance. There are like more than one of these tests, by the way. So a Kolmogorov-Smirnov test is another test that you could use for normality. I don't know why there's two people or two names for each of these. There's very few that do that, and then all of a sudden we get to a normality test and we have people pairing up to make one, I guess. But a Shapiro-Wilk test is going to be what we kind of do in this class, and that's going to be basically testing the null hypothesis that these residuals follow a normal distribution. Then we look at how well they do and put a probabilistic calculation of how often would we see this much departure from normality by random chance if this data really was normal. So our p-value, we're going to kind of judge it the same way, where a p-value of 50% means that we're performing exactly about how we would expect by random chance. The lower it is, the more unusual this is to see by random chance, if this is really normal. Now here's the thing though, when we have a low p-value, that gives us clear evidence that this is probably not normally distributed residuals. But if our p-value is, not particularly low, like it's 10% or 20% or 30%, well, it's not really telling us that the residuals are normally distributed. It's just saying that we don't have enough data to say that they're not. So we're just kind of saying it might be okay. We don't have any reason to say it's not normally distributed. So it's kind of the frustrating thing about hypothesis testing and statistics is we can never really conclude the null. We can never really conclude this is the parameter. Instead, we just say this is a reasonable, like this could be the parameter. This could be the truth. And our data is consistent with that if it was. Now, here's the thing about hypothesis testing again, and this is where we need to really remember this when we're doing these diagnostics. When we're working with small sample cases, it's going to be hard to reject, even if the normality assumption is false. If I only have 20 data points, I need to have some real abnormal residuals in order to have a low p-value here, because hypothesis testing is dependent on the amount of data I have. If I don't have a lot of data, it's harder to reject. So just kind of keep that in mind, that you may not get a super low p-value if your sample size is pretty small. And that's where kind of the residual plot or the QQ plot really helps, is because it can kind of help us see, yeah, this really looks like we have some departure from normality. Our p-value is about 5 to 10% or something, so maybe the normality assumption seems pretty suspect. Now, the flip side of that is the large sample case. And this is where we don't want to get kind of carried away by really small p-values, because we're going to very frequently see some super low p-values when we have really large samples. And again, it just means that we're confident it's not normal, but it's not, the p-value isn't telling us how abnormal it is, just how confident we are that there's at least some departure from normality. So if we have some mildly low p-values like 5, 10, 15%, when we have a really large sample, it's probably actually pretty close to normal. That if there is a departure, it's probably pretty small because we have a really large sample. So if that's the case, we're working with kind of several hundred data points, like 400, 500, 1,000 data points, and our p-value is kind of in that 5, 10, 15% range. Well, that's probably okay, actually. Like, if there is some abnormality, it's probably pretty small, because we have such a large sample that's happening with. So again, pairing these up with the visualization, I think, can kind of help complement the two. The weakness of the visualization is that it's kind of tricky. It's kind of subjective to be sure if we see abnormality or non-constant variance. The trickiness of the hypothesis test is that we're kind of limited to how small or large our sample is, especially the small sample case is kind of tricky to reject here. Really the same story for the Bruch-Pagan test. One extra thing I'll mention is that this particular function does require a package, LM test, that is a lowercase l, I believe, that you'll need to install first in the library. But again, it's really all the same stuff applies here. The null hypothesis we're testing is that the residuals have constant variance. The alternative is that they're not. And we want to be cautious about the p-values, especially in a small sample case, that it's going to be really hard to reject, even if there is a non-constant variance problem there.